Just a few seconds. Thank you very much. We can continue with our webinar.
Good morning, everyone, and welcome to today's webinar on AI X Climate Resilience. So I am Tyasha Naidu, CESA YPF KZN committee member, and I will be your facilitator for today's session. So today's session will be a panel discussion with a focus on how is AI reshaping the engineering practice. So specifically, how is it changing the way that we think about climate resilience? And how do we then implement that in the engineering workplace? So we have an esteemed panel, which consists of Omera Jajbay, so energy engineer at Sutari, Dr. Craig Tinashe Tanyaniwa, who is technical lead at water footprint implementation, Dr. Suleiman Salim Patel, lecturer and researcher in electronic engineering at UKZN, and Tasneem Esop, who is a manager in artificial intelligence at IQ Business. So I'm going to hand over to the panelists to give us a quick introduction of who they are and what they do before we jump into the panel discussion. But please remember to put in any questions or comments that you may have in the chat or the Q&A chat box at the bottom of your screen. Before we jump in, Omera, I would like to acknowledge our sponsors. So a huge shout out to our diamond sponsors, Kufanikiwa, Zutari, our gold sponsors, as well as our silver sponsors. And a huge shout out to SciEE, who have been our collaborators on this webinar. Thanks, Omera.
Thank you, Tyasha. Hi, everyone, and thank you so much for joining. My name is Omera Jajbay. I'm an energy engineer at Sitari, and I'm completing my master's in the optimization of renewable energy and energy storage systems in smart grids using artificial intelligence. Next slide, please. Okay, so where I currently see in engineering systems integrating with AI the most is on these large-scale integrated systems that are primarily solar, wind, and battery energy storage systems that are embedded within the evolving smart grids. So these systems are increasingly hybridized, forming virtual power plants that require real-time coordination, forecasting, and optimization. So my role spans the design, commissioning, and optimization of these systems across Africa and the Middle East. Next slide, please. Where climate pressures are really showing up is in the variability. So we are seeing more unpredictable irradiance patterns and fluctuating wind speeds. So if we look at our resource variability, such as solar irradiance and wind unpredictability, this will obviously impact our forecasting accuracy and our overall grid stability. It will cause over and under generation. Extreme weather and infrastructure stress also affects our generation. And to the surprise of those that are not in renewables, in fact, too much of heat can also reduce our PV efficiency. So certain things like flooding causes damage to our substations and our infrastructure. Our windstorms, they cause turbine stress. So all of this impacts, so all this climate aspects really impacts our infrastructure, and it degrades our system, and it increases maintenance. So it's no longer just enough to design using historical averages. We really need to design for resilient, real-time scenarios. So climate pressures are really showing up as uncertainty, stress on infrastructure, and we're seeing more weather extremes really affecting our asset performance and increased pressure on already constrained grids. So this really makes balancing the supply and demand significantly more complex, and it increases our reliance on storage and intelligent control systems. Next slide, please. Where I really see impact of AI on the systems that I work with is on the forecasting side. So we are using models like LSTM networks and other machine learnings to actually optimize our system to improve our dispatch planning and reduce uncertainty, to improve our forecasting. In smart grid optimization, we are seeing real-time energy balancing. We are using it for the dynamic dispatch of wind and BESS. We use algorithms like machine learning and optimization algorithms, and this increases our grid stability and it reduces the curtailment of renewables. AI is also very beneficial for predictive maintenance in fault detection and asset health monitoring. And of course, it plays such a big role in virtual power plants, where it enables decentralized systems to improve of a grid flexibility and resilience. And we use it as well for climate risk modeling, where we can actually try to forecast future scenarios, and we use it for long-term planning. So for me, the big shift is that engineering is becoming more probabilistic and data driven. So we are moving from a static design to an adaptive system. And in the context of climate resilience, that is not optional, that is essential. So AI is not replacing our engineers, it's helping us to design these systems that can actually cope with climate change. And climate resilience is no longer just about infrastructure, it's about intelligence. And AI is really bridging that gap between variability and reliability. Thanks, Diasha.
Hi, everyone. My name is Craig. As said on the slide, I work for the Water Footprint implementation as a technical lead. Can I have the next slide, please, Diasha? Yeah, so what we do at Water Footprint implementation, we work mostly in two streams. One is the water footprint accounting, where we help to quantify the total water consumption in industries, so across their supply chains, even for projects. Here we measure the blue water footprint, green and gray water footprints, primarily looking at the water abstracted or withdrawals, also looking at the pollution and revealing where this pollution and this abstraction is and how much water is consumed. On the other side, we also support companies by developing water stewardship initiatives in the specific basins where these industries cause the most harm. In line with best practices within water stewardship, we also enable these companies to address their unavoidable water footprint through targeted place-based interventions, such as wetland rehabilitation, non-water reduction within the basins where they operate or where their products come from. Next slide, please. So how do climate pressures show up in the water systems working? Well, the first thing is that most companies and most countries have carry water footprints from water scarce regions. An example being, if I use the Netherlands, which is where one of our offices is, a lot of the products that come into the Netherlands have got a virtual exported water. They get flowers from Kenya. They get wine from South Africa within the Western Cape region. And there you can see already that the Western Cape region is quite a water scarce basin. And what happens is that in these basins, it's already under risk. So if anything happens, like what we saw in the drought in Cape Town, you see that either the prices of goods go up in those countries that import a lot of water, or those services disappear. So they have to look at other supply chains and even look at whether they need to have these projects. An example being avocado, for example. Another case in point that I also use here is a lot of the cotton used in manufacturing, look at H&M and all the other companies, is grown in India's freshwater basins. And what we're seeing is a result of that and other factors there that India is having a lot of groundwater abstraction, causing less subsidence. But also what we're seeing from that is that in the instances where India doesn't get enough rainfall or there's not enough recharge, the cotton industry could likely be influenced or impacted. So that also shows up in the system of Lucano. So that's some of the examples that we have there. Next one, please. Yeah, and how do we see AI accessibility? For me and for the organization, there is a growing concern on how to use AI itself, but I'll speak about that later. But I think right now we haven't really started seeing an impactful decision-making ability of AI within our sectors, mostly because people are still quite reticent to use it, bearing in mind that our field is mostly about sustainability and not just wanted to show about the staple of AI. But we do see that our sector is quite reliant on manual data collection and conventional hydrological models, because when I mentioned, when you look at the water footprints of projects, we need to know the footprint of their agriculture, and that data is still manually collected. So the major shift that we're seeing here is that AI could be useful in synthesizing complex water use data sets, and it also could improve hydrological model in terms of being able for us to predict what could happen a bit better, we hope, and also being able to gap fill in some of the data scarce regions. But like I said, we haven't really gotten there yet. I've seen a few companies that are using AI to do that, but not yet. But then, like I said, just to wrap this up, is that the issue though is that the large data centers that we use to train AI consume a lot of water and a lot of energy. So as we adopt AI to solve our challenges, we're also trying to look at whether it is sustainable and how we can use more sustainable models or in-house models and not shift the burden into our basins and communities.
Hi everyone, I'm Tasneem Isap. I'm currently serving as a manager within AI at IQ Business. I think we can go to the next slide just to cover some of the rest of the point. Cool. So I essentially have a background in mechanical engineering and worked a lot in engineering consulting, and then moved into simulations engineering and software development with a huge focus in actually AI engineering and developing these AI solutions for different sectors. So thinking financial institutions, engineering, mining, retailers. And a lot of what we're seeing is both your proof of concepts, your enterprise grade AI solutions, your generative AI solutions, and even your machine learning, your classical machine learning solutions that are actually built on-prem. A lot of the AI solutions that we're noticing is they're essentially capable of all of your cognitive decision making. So leveraging computer vision, optical character recognition, like voice agents where you're able to interact with it, natural language processing as well. And essentially there would be some sort of problem that we're trying to address, whether it be a classification problem, whether it be a simulation problem, and essentially building out these solutions for these engineering companies and to solve the problems and allow the organization to get better efficiencies, better accuracy, and of course, time saving. A lot of these AI solutions that we're seeing being built to solve the problems within the engineering sector, they're more often than not either built on the cloud or they're, of course, leveraging their servers and databases that are sitting on-prem. A lot of the times we have a bit of a hybrid model where it's your IoT sensor data and information that needs to feed into a predictive system. And so it'll be a combination of both your cloud and on-prem models. But just to go a little bit into the systems on the next slide, what we're seeing is a lot of different engineering systems that are coming together, and AI is essentially serving as that orchestration layer, connecting all of the different systems, all of the big data that we're seeing across these systems and turning it into insights and actionable decision making. So in terms of the engineering systems that I'm actually seeing within the engineering sector is you have your IoT sensors, you have a lot of sensor information and big data that is sitting within machineries and within equipment in these organizations. We even have normal simulation software or design software that's sitting on each of the employees or design engineers' computers, so things like your SolidWorks, your ANSYS, etc. And then moving into more of the organizational back-end processes, we're seeing your enterprise resource planning systems, your CRM systems, SAP, etc., all sitting at the backbone of this. And what AI is actually enabling is connecting all of these engineering systems, connecting the whole enterprise back-end and front-end systems. So not only enabling sales, but also enabling efficiency within the back office. We're seeing an end-to-end digitization of all of these processes within organizations. And I think that feeds quite nicely into solutioning for climate pressures. So For example, in the mining sector, I mean, there's natural disasters, there's extreme weather disruptions, which Omera covered earlier, extreme heat, which is affecting different machineries and different components. And then that ties quite nicely into the engineering systems, the sensors, informations that we're seeing, able to detect these climate pressures, able to, and leveraging AI to utilize this big data, turning into actions where you can do maintenance and predictions on, for example, when to replace a specific machinery or when to predict a specific failure pattern. So we're turning all of these data points into actual insights, which feed downstream into further processes. So, for example, your supply chain process, detecting those political changes, sourcing constraints, demand changes as well, and feeding that into actionable insights. One of the main AI influences that we're actually seeing is AI essentially enables organizations to adopt it for increased efficiency, accuracy, compliance, and resilience. So all of those different predictive maintenance decisions that you're seeing on screen, automated engineering design, digitized cognitive workflows, what that's actually doing is enabling organizations to embed AI within their processes and get better efficiency, accuracy, and a resilient organization that's completely digitized and able to use AI to their advantage and to make everything quicker and, of course, more compliant and more resilient overall. Thanks, everyone.
Good morning, everyone. My name is Sulaiman Salim Patel. I am a lecturer at the University of KwaZulu-Natal in electronic engineering, and I overlap quite a lot into the computer engineering space as well. Next slide, please. So my position at the university spans both being an academic, being a researcher, and being an engineer. At undergraduate level, I work a lot in the design streams with electronic and computer engineering, where we run projects that have increasingly a focus on sustainability and green technologies, such as the development of pilot AI for leak detection in pipeline networks. And one of the more recent ones that was conducted last year was a automated waste sorting smart bin for separating waste streams at source. In terms of my research profile, I am associate member of the KZN Sustainable Transportation Research Group, which is currently involved in a number of projects with the Department of Transport on AI for resource allocation, load balancing, and enhancing cybersecurity, particularly in vehicle-to-anything IoT systems and AI-based pavement defect detection. I'm also collaborating with the UKZN WASH Center around edge optical character recognition for retrofitting onto digital and analog legacy meters and getting some of that data into the IoT ecosystems. On the consulting engineering work, I have been involved with JG Africa, the Department of Water and Sanitation, and the Water Research Commission on a project around the South African excreta flow diagram, or SFD. And most recently, we put together and finalized the digitalization framework that will hopefully be driving the strategy for how the SFDs in South Africa are going to be digitalized and made more resilient in the future. Next slide, please. So my role is primarily in the building of human capacity around climate resilience. And what we're seeing as educators and researchers in the space is that the critical challenge is developing engineering students who have an awareness of sustainability and who are competent and cognizant of the environmental cost of their engineering actions. And that is linked to developing the knowledge and behavioral competencies that are aligned with EXA's graduate attribute expectations, particularly graduate attribute number 7. Linked to that is the idea of developing authentic intelligence alongside artificial intelligence. And by that authentic intelligence, I mean developing young engineers who are truly masterful at their engineering trade. And we don't want to reach a stage where there's an artificial intelligence glass ceiling on human development. Increasingly, we find that one of the big risks with AI is that because it can generate answers so quickly, a lot of junior engineers end up taking shortcuts. They end up looking for quick wins, and that leads to inhibiting their ability to develop deep understandings and heads towards a knowledge ecosystem that is increasingly reliant on AI tools. And as a result, the authenticity and expert knowledge that's required of an engineer isn't being developed at the correct rate. So we are looking at, in the universities, creating ecosystems around responsible AI use that prioritize critical thinking and healthy skepticism. And whether working with students or working with industry, the sort of philosophy that we've been driving is that AI is a powerful tool or a well-read intern. It cannot be considered just another expert, and it is certainly not able to replace humans.
Thanks, everyone. So that was really insightful. And what I can see is that each one of you have such diverse, unique experiences. And that's what I want to kind of merge in today's panel discussion. So I want to be able to bridge together all of your experiences in AI, energy, water, academia, to kind of start the discussion. And I hope that the attendees can feel inspired after this. So maybe to start, within how AI is showing up in the engineering practice. Omira, let me start with you. So from your perspective, where are you noticing the biggest changes in how engineering work gets done because of AI?
Okay. I think the biggest shift I'm seeing is currently in forecasting and planning, because now we are using models like machine learning to predict generation on an hourly basis and sometimes even probabilistically. So that completely changes how we size storage, for example, how we plan dispatch, and even how we evaluate risk. The second the major change I would think is operational decision making. Okay, because optimization used to be rule based. For example, when you have PV during the day, you charge the battery and then you discharge it during peak hours or at night. Now, with AI-driven algorithms that can adapt in real time based on forecasting uncertainty, on load changes and grid constraints. So it's much more dynamic. And another major change I would say I noticed is the speed and scenario analysis. With AI assisted modeling, we can now simulate multiple climate and demand scenarios much more efficiently. So that allows us to stress test systems against extreme weather variability, predict future climate projections. And in the past, that level of analysis would have been so time intensive and sometimes not even feasible with project deadlines. But if I really think about it, I think the biggest change, perhaps, and the most important shift is in the role of the engineer. AI hasn't removed the engineer from the process. It's elevated that role. So we are now not just responsible for the physical system design, but also for validating these models and interpreting its outputs, for questioning biases in data, and ensuring that the decisions remain technically sound and grid compliant. So I would say that the engineering decisions are moving from deterministic to probabilistic. Now we are working increasingly with multiple scenarios, distributions, and probabilities rather than single design points. And the pace of iteration has just significantly increased. So these tools are really allowing us to evaluate options faster and raising the quality of solutions that actually reach clients. Another aspect I would think is that the cross collaboration across disciplines is becoming more data driven. So the AI tools really are creating shared platforms of insights that allow electrical, civil, mechanical, environmental, and all of us to really work from the same evolving picture. So from my perspective, the biggest change isn't automation. It's that engineering has really become more predictive, more data driven, and more interdisciplinary. And in the context of climate resilience, that shift is critical, because resilience isn't just about designing for the average anymore. It's about now designing for uncertainty. Thanks, Dasha.
Thanks, Omira. I love that. And I love how you say that we do need to work together with AI, and it's not replacing the engineer. So Craig, I'd like to then build on that a bit. So when you think specifically about climate pressures, variability, the extremes that we have, and long-term change, where does AI seem most useful then for you?
Thank you. I think Amara put it quite well when she mentions like how AI is being used now, to use mostly probabilistic modeling. I think when I look at it from our perspective, or my perspective, which is the civil engineering perspective, is that with climate pressures, I think we already experiencing them. We kind of know how to design for them, but we don't have the data to do that design. I'll reference when I was doing my work in my PhD with future water. One of the things I was doing was trying to model how infiltration in a detention pond would change under varying rainfall characteristics. And of course, I was able to use the different climate models that have been developed to date. But we still had some issues with the data in terms of how do you find the appropriate infiltration rates, how do you find the rainfall data? So we had to actually set up a rainfall station. And I knew that from hydraulics was an easier way to try and find multiple stations and try and interpolate what those stations would be able to do. But like the time to do that within the software I was using took a lot of time. My model ran for 3 days before I could get an answer, for example. So where I think AI could be useful, at least in my context, is that it can reduce that compute time, assuming that it is programmed well, because at the end of the day, the way we're using AI now through LLMs and agentic AIs is they're still models, and they're based on the input data, and garbage in is equals garbage out. So they still that caveat you have to put there. But I think just to wrap my answer up is that the best use under climatic pressures would be in data gap filling, in probably helping a designer to come up with a faster way to do your scenario analysis, come up with a better way to do your, in terms of maybe creating a spreadsheet for you if you're looking at it from the civil engineering, which is still quite Excel based, unfortunately, or if you want to plug it in into your software, or for those who can't code, if you want to use it in your to get your Python code for your position, for example. So I think that's where it probably would work best for a typical engineer and how to address the climatic pressures that we face, which I still think for us is largely data constraint.
Mm-hmm. Thanks, Craig, and that was a really interesting response. So I want to also go now to Suleiman, and just shift the focus a bit from AI and the idea of climate resilience. So if I had to ask you, Suleiman, to what extent in engineering is there a shift from designing for known risks versus how to prepare for the unknown or evolving ones? As Craig mentioned, data gaps is quite important. So how would you respond to that?
Thanks, Diasha. I think Craig actually summarized the biggest challenge and the biggest danger with AI as garbage in, garbage out, which I 100% see in the space. AI, for many engineers who are not in core computer engineering, is viewed very much as a black box where it receives inputs and produces outputs, and the quality of the input then drives the quality of the output. And what is a limiting factor in this sort of use of AI is that we have a very mature understanding of physical risk. We understand vandalism, we understand tampering, we understand how this manifests in engineering, and we design around that. But from the IT and data side, the lines between traditional IT, cybersecurity, data governance, and related concepts and engineering are now becoming very blurred. And we are entering into a space where there's not enough regulation, and the regulation around the use of data is not evolving at a pace that can keep up with the technologies. So you're seeing legislation coming out like protection of personal information. We've got our national data and AI policy. We've got increasingly more guidelines around how to work with AI, but the tools are outpacing the rate at which regulation and frameworks around governance can be developed and approved. And the big risk that we see around this is that, well, yes, we do need to, and we do want to use AI for improving decision making, but we don't want to compromise our systems. If we look at what's happening globally, especially in places like the Gulf with the ongoing war, we see that infrastructure is a national asset that is being targeted as part of the ongoing conflicts. And should South Africa ever be in a similar position, it is much easier to see the physical targeting of infrastructure than to see the cyber attacks and the cyber targeting of infrastructure, which undoubtedly happens behind the scenes. So we do need to also, as we work with AI systems, as we drive decision making in the infrastructure space and in engineering, catch up to the regulation of it so that we are not exposing sensitive data which could become malicious and could become massive vulnerabilities for our nation if abused or if compromised in the future.
Mm-hmm. Thanks, Suleiman. And I think you touched on a really important point, which is legislation and regulations. And we typically tend to always focus on the positives, but some of those risks are also really important to highlight. So Tasneem, maybe now shifting to you. So as systems become more predicted and automated, where do you see engineers remaining essential in ensuring this type of resilience? And with that, what must we as humans do to interpret, question, or decide what types of models that we can or cannot use?
I think that's a very good question. It's quite important to the engineering profession as a whole. Essentially speaking to the compliance element that Suleiman mentioned, even speaking to the big data element that Omira mentioned as well, and making sure that the risk isn't necessarily that AI replaces engineers, but that we find a middle ground where you're leveraging the human expertise, the domain knowledge that we already have, and embedding it or leveraging the AI capability to do things quicker. So again, speaking to Craig's point where, again, it is a bit of a black box, and sometimes engineers are using AI models to help them with the coding or to help them with reporting or comparisons, etc. But it's a very data in, data out, garbage in, garbage out sort of flow diagram that essentially exists. What I'm actually seeing is that the most resilient systems is when there's a human in the loop. So you're keeping that domain expertise within that process whilst leveraging AI for that speed, a bit of more efficiency, double checking, accuracy, etc. Because what essentially engineers are irreplaceable for is things like that contextual interpretation and that domain knowledge. Essentially, if you're leveraging Gen AI, you're going to have to prompt it. There is still a human being prompting it. So again, that domain knowledge is still feeding in. But AI models are only as good as the data that they're trained on and also the data that they're linked to or referenced on. Whereas an engineer would understand that local condition and domain knowledge. In terms of things like your ethical and risk decisions, of course, deciding what's an acceptable risk threshold or trade-offs between safety and cost, that's when the human in the loop needs to come in as well. So ensuring that the systems that they build are resilient for their engineering problem or for their process. And then also things like your model interrogation and validation. It's very easy to get AI to test AI, but at the end of the day, an engineer must ask and scrutinize, does this prediction actually make sense? Is this AI model or AI output actually acceptable? Is it meeting the threshold? And that's where that deep domain expertise remains critical in the entire process. And of course, things like your stakeholder communication, things like that human interaction, that's still where that engineer would remain crucial in the requirements gathering and crisis response, adaptation, etc. because at the end of the day, the models cannot fundamentally decide what's the safest threshold, what's the trade-off between the safety and the cost. That's something a human being needs to take accountability for, and of course understand the social, political, and climate implications of that. And that's where you have to keep in mind what data you're feeding in and what are you allowing the AI model to decide for you versus what are you actually deciding as an end-to-end solution as a human being with all of these thresholds, with all of these risks that you're considering as well. And the benefits of it will be this end-to-end human and AI collaboration that's solving a specific problem, whatever problem it might be. And of course, building in that resilience, that efficiency, and keeping in mind the risks associated with using AI in that process as well.
Mm-hmm. Thanks, Tasneem. And I think you touched on a really important point. I mean, there's so many different factors that contribute to, safety costs, as you mentioned, and it needs to be a collaboration. So thank you for that. I want to then move on to Craig, just as we touch on leadership then, and how do we actually affect change in these sorts of industries? So when decisions are informed by models, predictions, and probabilities, how does leadership then change?
Thanks for that. I think, it's something that we've been, in my new role with WFI, something that I've been dealing with is when we present findings to our clients, most of our findings are based, like if it's a water footprint assessment, sometimes we have to model their water system, or if it's a water stewardship project, maybe that's looking at how a certain project will reduce non-revenue water losses or we improve their water quality. It is a modeled result. And we're then asking these entities to commit resources based on these models. So with that, we say that the shift in leadership has become less about having a definitive answer to say, well, if you do this, this is what you get. But now it's to do it more with variability and predictability to say, well, this is the answer we have, and we're honest about the uncertainty. Now, in engineering, that's not always the easiest thing to do because your project doesn't really have, or your project budget doesn't have a lot of leeway. You can't say you're designing a pipe that's either 250 mils or 100 millimeters diameter because no one will give you a budget that wide. So you compromise and you find your best fit, but sometimes you over design. So I think maybe just to say that the temptation that I've seen is that people want to give answers that have been modeled and present them with authority to say, we have designed this greenfield and we found that you need to have X pipes, you need to have X pumps, your reservoir must be this big, and you then lay out your assumptions. But we usually don't say that, well, the model says this and this is what you do. We say that as engineers, this is what we're saying. And I feel like now with the coming of, with the decision being more model informed, is we need to be a bit more honest and not hide it within the, what do I call it? Within the fine print of our design. And also not try and over-engineer so that we never fail. So I think practically this means that we need to have decision makers who are more comfortable with probabilistic thinking, who are less comfortable with false precision, and we need to be responsible with how we communicate our findings, and we need to be also responsible with our uncertainty and not buried appendices. And in academia, that's quite a established thing, but within the field, not really. And even now with our engineering design, I think you've seen that there was another incident that happened that X mentioned. And some of those are coming from us not being clear about our assumptions. And now we're going into a very assumptive period of engineering with AI and with all these other models. So I think that is how it's going to change. State your assumptions first, say your results, and then say what it means on the budget, not say the results and then assumptions like what we used to do.
Mm-hmm. Thanks, Greg. I mean, you are going to definitely have some trending keywords here. State your assumptions, garbage in, garbage out. But that's great. So I just want to move on to then Omaira. So for engineers currently working in industry, what kinds of learnings or adaptation systems do you see as most important right now? And where do you also see professionals needing to stretch or evolve in this sort of space?
Okay, thanks, Tasha. That's a very good question. I think the engineering profession is at a genuine inflection point. The skills that defined an excellent engineer a decade ago are still necessary, but they are no longer sufficient. Engineers who want to remain relevant and effective in this world that is being shaped by AI and climate really need to stretch in several important directions, if you ask me. I don't believe we need to become data scientists, but we do need to understand the fundamentals. How does AI work and machine learning at a conceptual level? What can it do for us and what can't it do? How can we train them and where do they fail? I mean, without this, we can't really responsibly interrogate the AI tools. If we don't really understand how the models behave, we risk either blindly trusting them or rejecting them out of discomfort. And neither is good engineering. So the second area I feel is the to adapt to this is system thinking. So climate resilience, if you think about climate resilience, it requires us to think beyond isolated components. It's no longer about us just designing a solar plant or specifying a battery. It's really about understanding the entire system. How does the grid interaction work? What are our regulatory constraints? What's the climate variability? Suleiman touched on cyber risk, which is so important, and also the long-term operational strategy as one interconnected system. So we as engineers definitely need to stretch beyond our discipline silos. We need to become comfortable with making decisions under uncertainty. Deterministic design standards that underpin most engineering practices were developed for a stable world. But now everything is variable. As climate variability intensifies, we as engineers need to become more comfortable with working with probabilistic scenarios and updating our designs as conditions evolve, and honestly communicating honestly to our clients. There's obviously always the human decision about communication that Tasneem touched on. As our AI becomes embedded in the engineering workflows, we must be able to explain these complex models to non-technical stakeholders, our clients, our policymakers. We don't just deal with engineers, we deal with everyone. The decisions we make affect even the public, of course. So we need to be able to explain this, understand our decisions, and be able to really translate the technical outputs into strategic decisions. And that is becoming a core skill. So EQ has always been relevant, but it is becoming so much more important in this age of AI, especially as AI takes on a more specialist computation a role. Engineers will increasingly be valued not just for our technical ability, but for our ability to lead, to communicate, and to make high-level technical decisions, not just performing calculations. So I don't think the future engineer necessarily needs to code neural networks, but we do need data literacy, system level thinking, be comfortable with uncertainty, and definitely stronger interdisciplinary communication skills. So the professionals who will evolve will be those who see AI not as a threat, but as a tool. And that will ultimately thrive. These are the engineers that will thrive, the professionals that treat this as an ongoing learning practice, not as a phase or, our learning hasn't been completed in university. We're constantly learning. So I think that's basically very important.
Thanks, Omaira. And just so I want to get your opinion, Suleiman, as Omaira is speaking about the engineer from an academia perspective. How do you think the role of the engineer is evolving as systems become more data rich and adaptive?
So I think the word probabilistic has been thrown around a lot today, and that really sits in sort of contrast with the standard curriculum and the standard way that engineering has been developed. If we think back to the way traditional engineering curriculum was designed, it was very focused on calculus and mathematics, but a smaller emphasis by comparison was placed on statistics and on really understanding how to deal with uncertainty. When we look at the landscape and the way it is evolving, what I see happening increasingly is that AI as a tool can be adopted in a variety of contexts, whether it's an analytical tool, an ideation tool, a writing tool, a development tool. It's used as a very fundamental part of our engineering toolkit, but contextualizing and understanding how the uncertainty is related to its use in the different facets of engineering is understood. And I see there's a comment in the chat around 90% accuracy and the performance metrics that are associated with AI, but there's not a lot of literacy and a lot of education around how to truly interpret these performance metrics. Because if I paint things in a slightly different light, when you look at AI for anomaly detection, where anomalies have a 1% chance of occurring, your AI, by the nature of the problem it's exposed to, is going to expect to say that you don't have an issue 99% of the time, because the probability of the anomaly occurring is that low. So that is not good AI. That is just the nature of the problem. And the statistical literacy that is required to truly understand how to evaluate and measure AI performance is something that the field is still grappling with, is still developing, but that historically wasn't given the level of importance and the level of exposure that the world currently now needs.
Mm-hmm. That's a really interesting point, Suleiman. So I want to now just touch on some of the questions in the chat, the Q&A chat box that have been asked. So I'm going to start with Bashan, who had a question on, so he says, AI solutions themselves can impose internal environmental costs. For example, the cost of training an LLM. Has anybody looked at the cost-benefit balance? Can AI cause negative climate impacts? So the discussion seems to contextualize AI as being only beneficial. But I think, so Suleiman, you also did touch on a lot of the risks. Is there anyone on the panel that would want to touch on this a bit more?
Yeah, Tasha, I think I'll take that one because it also ties in. I see Tremaine had a question for me regarding AI uses a lot of energy and water. So is it really worth it? And is it more sustainable? Can we make it more sustainable? So that definitely ties to Barshan's question. And I completely agree. But let's just understand, right? AI uses a lot of water and it definitely uses a lot of energy. So where does it use this water? For the cooling systems to prevent overheating, and it uses electricity generation. Now, if this electricity is not clean, then of course it's going to have a carbon footprint. And training large AI modules, definitely it consumes millions of liters of water, depending on the size of the model, the location of the data center, and the cooling technology concerned. And this is definitely a concern with AI because the data centers are often located in water-stressed regions, so it competes with local water needs, and that may increase your energy it might become more energy intensive because it increases your emissions if they are powered by fossil fuels. So yes, AI definitely has a real environmental footprint, but does it still have a benefit overall? So AI has both environmental cost and benefits. The key question is whether the net impact is positive. Okay, so we have to look, where does AI help the environment? In energy efficiency, where we're optimizing power systems, we're reducing waste and losses. In renewable energy, where we're making our systems more scalable, more reliable. It enhances higher penetration of clean energy, where we can better predict our climate risk. It supports adaptation planning. And of course, AI has its negative impacts where it consumes a lot of energy, it uses a lot of water for cooling, and it will have a carbon footprint if it's used by fossil fuels. So the key idea is AI efficiency versus AI footprint. If it reduces more emissions than it creates, and it improves the system efficiency significantly, then it is net beneficial. Okay. And what I see that what the industry is trying to do is that, so how can we actually tackle this? So let's try to move our data centers onto renewable energy. So we are producing clean energy, we are reducing our carbon footprint. Let's try to use air cooling and recycled water systems. So we reduce competing with local communities for water, and also improve the model efficiency itself, make the model smaller and smarter, as well as locating these data centers in cooler climates. So AI is not inherently sustainable, but when applied correctly, especially in energy systems, it can deliver net environmental benefits that far outweighs its resource use. Yeah, that's my answer. Thanks, Tiasha. I hope that answers the question.
Thanks, Amira. So there is another question from Bashan as well. Speaking of if problems are cast in the probabilistic space, as you mentioned previously, Amira, how do we ensure robustness? So engineering curricula emphasizes robustness in a traditional sense, but stochastic robustness is uncertain. So how do we deploy dependable probabilistic models? Who would like to take that?
So I don't mind taking that one because it's a very simple answer. The answer is we have to research proper ways of doing this. As we spoke earlier, historically, this hasn't been core and central to the way engineering has been taught in the curriculum. And I touched on the fact that statistics compared to calculus and other fields of mathematics is underrepresented in the engineering curriculum. So when we look at how do we quantify uncertainty, how do we deal with uncertainty, and how do we then develop our AI at a level that its maturity is appropriate for use, that's actually one of the big open AI questions in the academic space around, finding the appropriate frameworks, because the statistics is there, the mathematics is there, but engineering has always been about applied maths, applied stats, applied physics. And the open problem is now moving into the space of, well, what are the appropriate ways to do this?
Mm-hmm.
Yeah.
Thanks.
Tasha,
Great.
and I want to, I think also mentions statistics, which is what these models are based on, is a largely misunderstood concept, even with the public. So the first example I give is when someone says there's a 30% or 20% chance of rain, and then people say, well, it didn't rain today. I think because no one has ever communicated that rainfall forecast says that all the simulations that have been done, 20% or 30% of them are say it's going to rain. That's what that statistics mean, but no one understands that. So to take that type of thinking that people have and apply to say, how can you make AI more robust? Currently, like I would say currently, what we're using is a black box, like everyone's been saying, and I agree, Simon, we need to do more research into it. But I also think we also need to be honest with ourselves in that there is a limit to which we can use AI engineering. And I think we need to find it and define it and never hard stop. Because there is a point where we can't use it in engineering as much as we wish to, but there is a point where it should stop. And I think that's why many people, someone in the question says the conversation has been largely positive, is that I don't think we currently know what the limit is. And until we know it, maybe we put caveats to it.
Yeah, and if I can just piggyback off what Craig said there, another very important thing when it comes to AI is this notion and this concept of overfitting. And from a technical perspective, what overfitting means is that the AI has learned historic patterns, but it has not actually learned the underlying understanding. So when, as an AI or as a computing researcher, you see models overperforming, your statistical background should actually be raising alarm flags to say, this is not actually something that can adapt to new information. It has actually only learned to pattern match against what it has been exposed to, and is actually useless. And that presents a very important point, which is not well understood, which is statistical uncertainty actually, to a degree, represents robustness in the AI context. And it seems very counterintuitive that we want to say, well, we do not want our models to be too accurate because that means they haven't learned anything. But that's the equivalent of saying that we have a student who can regurgitate the textbook, and when they come in as an intern in the engineering practice, give them a new problem and watch them flounder for a few days without knowing how to do anything.
Thanks, Sulaiman. And I think very interesting discussion and conversation. And I think when a 1 hour slot was definitely not sufficient for this type of discussion. But I see there are a few more questions in the chat box, but just because of time, I am going to stop there. We will be able to answer your questions after the session in the chat, but you can reach out to any of our panelists via email or LinkedIn. We will share the recording and details afterwards if you would like to get any more information or have any more questions. But I am going to close there. So thank you all for joining. Thank you to our wonderful panelists for sharing your incredible insights. I think it was a really informative discussion. And I hope you guys can join the next one. Thanks, everyone.
Thanks so much, guys.
My
Bye.
pleasure. Cheers. Bye.
Thanks.